Welcome back for more significant roulette. In the first video, I discussed the typical experiment, two groups of 32 with a true population effect size of half a standard deviation. Here's the distribution of the p-value for that typical experiment, and those values distributed around a roulette wheel. This article discusses the distribution of the p-value. Running this roulette wheel is exactly equivalent to running this typical experiment. 0.09, approaching or perhaps running away from significance, but by a simple random flip of the wheel it could have been 2 stars, or 0.12, or 3 stars, or 0.6. Any individual p-value seductively suggests certainty. There's definitely an effect. There's no sign of an effect at all. But in fact, a p-value tells us very little indeed. A p-value is simply not to be trusted. By contrast, the confidence interval is highly informative. Our best estimate of the true population value is about 13 here, our point estimate, and the interval runs from about 3 to 23, indicating the extent of uncertainty in our result. Compare this with the p-value, which is a single number which offers seductive but illusory certainty. The extent of uncertainty is made salient by the confidence interval, and we need to hear that message. We've been assuming that we know the true difference in the population, and we can mark that with this dotted line. So when we run down the dance of the confidence intervals, we see how these successive sample results bounce around either side of the true value, and we can look here at the sampling distribution of the sample means. Incidentally, our statistical model assumes normally distributed populations, random sampling, and that the standard deviation in the population is known so that all these confidence intervals are the same length. Now let's change our focus and assume we have just a single result, and rather than knowing the true value, we want to discuss what the next replication mean would be. And in fact, I can tell you what that distribution of the next replication mean will be, knowing only this result. I'm changing focus from the distribution of sample means in relation to a known true value to a distribution of the next sample mean if I only know this first one. To say that differently, here I'm focusing on these solid lines, which are the successive sampling errors of successive results in relation to the true value. Now I'm changing focus to these differences between successive replication means. There's greater uncertainty in these differences because there's uncertainty at both ends, compared with down here there's uncertainty only at one end. And so this distribution is going to be wider, in fact about 1.4 times as wide as the distribution of these sampling errors. In other words, back here is the distribution of sampling errors when we know the true value, and here is the distribution of differences between two successive replication means centered on the first one. Now let me remove this assumption that we know what's going on and display a replication mean. So after obtaining this result, we might, for example, obtain that one. And if so, the p-value is 0.001. Or we might obtain this one, or this one, or this one, or this one. And you can see the p-value changing accordingly. This pink distribution here is the distribution of these next replication means. Most likely we'll get a mean quite close to this first one, but it could be a little bit above or below, or just possibly very much above or below. For any of these replication means, we can calculate the p-value as we have here. So, knowing the distribution of the next replication mean, we also can work out the distribution of the replication p-values. Knowing just a single result, we can calculate the p-value distribution for a replication mean. I've been assuming that we know the result of an initial experiment like this, but we can do better. For a start, I can remove the units. But further, all I need is the p-value from an initial study, because the p-value reflects exactly how the confidence interval falls in relation to the null hypothesized value. If you tell me that your initial experiment obtained p.05, then I know that the confidence interval just touches the null line. If you tell me that it obtained 0.01, then I know that it's a little distant from the line, exactly like that. So give me your p-value. I know where this confidence interval falls, and I can display the distribution of the next replication mean, because that's determined by this confidence interval, and I know the sort of replication means I'm going to get, and so I can determine the distribution of these replication p-values. Note that a result like this might come from an enormous experiment, very large n, with a very small effect size. Or it might come from a modest size experiment giving a quite large effect size, just depending on what this scale is here. But in either case, the p-value determines how this confidence interval falls, and so we can work out the distribution of replication p. Let's look at some probability distributions of the p-value. Here's the distribution for the typical experiment that we saw before, 2 groups 32, when we're assuming we know that the population effect size is half a standard deviation. Now I'll turn on the probability distribution for replication p after an initial experiment that obtained p.05. Incidentally, all my analysis assumes all p-values are two-tailed. So this blue curve tells us the distribution of the p-value we'll get when we do a single replication of an initial study that obtained p equals 0.05. I don't need to know anything about that initial study, its sample size, its power, the true value of the population effect size. I simply need to know that the replication will be identical with that first experiment, except with new samples. Now, as we did before, we can divide this area under this replication p distribution into 38 equal areas and label these, and there are those 38 p-values. So we can make up a roulette wheel for replication p following p.05. Now what about following p.01? There is the distribution. As we'd expect, it's lower down here at high p-values. We're more likely to get smaller p-values following an initial experiment that obtained p equals 0.01, but there's still very great spread in these p-values. And again, we can work out a roulette wheel for replication p following an initial experiment with p.01. Here's the distribution once again of the p-value for our typical experiment. And here's the distribution of the p-value for a replication following an experiment that obtained p equals 0.05. Somewhat similar distribution, and the most striking thing is the very wide range of p-values, now 0.01. And there's the distribution for replication p following an initial experiment obtaining p equals 0.01. Compared with 0.05, you'd expect rather more smaller p-values, rather fewer p greater than 0.1, but we've still got an enormous variability of p to be obtained by replications following an initial experiment with p equals 0.01. Back to roulette wheels. Here is the wheel we saw before for our typical experiment, and the distribution of p-values on the wheel for that typical experiment. Following an initial experiment obtaining p equals 0.05, here is the wheel, and again the distribution we saw before of p-values for this particular case. Following an initial experiment with p equals 0.01, here is the roulette wheel for replication p, and again the distribution of p-values represented on this wheel. This article explains the formulas underlying these distributions. Spinning this wheel is exactly equivalent to replicating an initial study that obtained p equals 0.01. We've been lucky and got 3 stars, but just by the flip of the wheel we might have got 0.9, or 0.08, or 2 stars, or 0.051. No single result from a wheel should instill in us any degree of certainty or confidence. Just don't trust a p-value. And now for a final way to represent the enormous sampling variability of the p-value. Here's the probability distribution of replication p following an initial experiment that obtained 0.05. Let's think about the area under this curve and think of the 10th and the 90th percentiles of this distribution. There they are. The 10th percentile is at 0.302 and the 90th at 0.65. This means that 10% of the area is to the right of 0.65 and 10% to the left of 0.302 in this invisible, tall, narrow, white area to the left of the blue. The blue is the middle 80% of the area under this curve. This means that on 80% of occasions, if we replicate a 0.05 experiment, we'll get a p-value somewhere between 0.302 and 0.65. On 10% of occasions, we'll get a bigger p than 0.65 and 10% smaller than 0.302. A very long interval. And this is the prediction interval, the 80% prediction interval for replication p following an initial experiment getting 0.05. There's another thing this distribution can tell us. What's the probability that a replication will be statistically significant? That's the area under the curve to the left of 0.05. I'll actually mark the area to the right of 0.05, and that area is 0.5. So there's a 50-50 chance, just a coin toss, that a replication following p equals 0.05 is statistically significant because it gets p less than 0.05, or it obtains p greater than 0.05. Now let's consider replication p after 0.01, and here is the curve we saw before. And now the 80% p interval runs from 0.401 up to 0.41. So there's a 10% chance, if you replicate after 0.01, that you will get p greater than 0.41, 10% less than 0.401, and an 80% chance that your replication p will be somewhere between these two values. So I can say the p interval, the 80% prediction interval for replication p, runs from 0.401 to 0.41, following an initial experiment getting 0.01. This curve can tell us our chance of obtaining statistical significance on a replication. Here I've marked the area under the curve to the right of 0.05. It is 0.33, meaning that an initial study that obtained p equals 0.01 has a 1 in 3 risk that a replication will give p greater than 0.05. Simply because of sampling variability, there's only a 2/3 chance that a replication will give 1 star p less than 0.05 following an initial study with p equals 0.01. P intervals tell us that if you replicate, you're likely to get a very different p-value. Here are some example intervals. We've seen the intervals for 0.05 and 0.01 already. As p-values decrease, then as we might expect, these values decrease as well. But these are all very long intervals. For 0.001, the p-interval tells us there's fully a 10% chance that a replication will get p greater than 0.14. You can think of these intervals as indicating the extent of uncertainty in a p-value. In a way, these intervals are a bit like error bars on a p-value, long error bars. Here are the probabilities that a replication will be not statistically significant. We've seen the values for 0.05 and for 0.01. For 0.01, there's fully a 33% risk that a replication will not even achieve p less than 0.05. Perhaps even more surprising is that following p equals 0.001, there's fully a 17% chance, a 1 in 6 chance, that a replication will not achieve p less than 0.05. Conversely, for a non-statistically significant result with p equals 0.2, there's a 1 in 3 chance you will get statistical significance. I've mentioned this
paper. It includes all the formulas I use to calculate these values. I'll also mention the research of Jerry Lai. Jerry found that researchers tend to severely underestimate the extent of variability of p-values. They severely underestimate the length of p-intervals.
I've looked at the enormous sampling variability of the p-value in 3 different ways and represented it by the dance of the p-values, very wide, significance roulette, an enormous variety of values on the wheel, and p-intervals, very wide. A single p-value, perhaps reported to 2 or 3 decimal places, offers seductive but illusory certainty. The confidence interval is much more informative and makes the extent of uncertainty salient. And I'll mention again our introductory textbook that emphasises estimation and open science all the way through. We do explain p-values, but you don't need to use them at all. Will you help us introduce the post-p-value research world? Let's close with some more significance roulette. You've just run a study and have calculated p equal 0.05 and you want to replicate. Let's do that. Spin the wheel in with the ball, holding your breath. Where will it land? 0.280. But remember, rather than just spinning again and hoping that you will get significance eventually, just by a flip of the wheel, it could have been 3 stars, or 0.2, or 0.04, or 0.33, or 2 stars. Yes, indeed, the roulette wheel tells us that you just cannot trust any p-value.